Hello, I'm Lana Saxonov. Today we'll look into what Onshape has to do in order to add a feature.
And I'm Ilya Barin. Lana and I were the first people Onshape hired almost 10 years ago, and she and I designed and implemented a lot of what we're going to be talking about today. Last year, I did a different under the hood session where I talked about Onshape's architecture in broad strokes. This talk is quite different, as we'll focus on a single operation in depth rather than on the high-level picture. After this talk, if you haven't seen it yet, you can go back and watch last year's. The operation we'll talk about is adding a fillet to a part in a part studio. What makes filleting special? Nothing. And almost nothing of what we'll talk about is specific to fillets, but we had to pick an operation. So you have an edge pre-selected and you add a fillet. Watch the animation and don't blink. Did you see that? Here it is again. So in this scenario, Onshape took less than a quarter of a second to respond. If Lana and I were to describe everything that happens inside Onshape during this time in full detail, it would take us days, and that would be exhausting for everyone. So we'll present a simplified picture. And one simplification that I'll announce right away is that in the video, you saw 2 clicks, one to create the fillet and one to commit the result. And in the talk, we'll pretend that this is a single operation. A simplification we won't make is collaboration. There is a collaborator looking at the same part studio in the same workspace at the same time. In this screen capture, it's just a second window on my computer, but in real life, it may be an engineer across the world. And the window on the right shows what the collaborator sees when the edit is made in the window on the left. Again, don't blink. And here it is again. So the collaborator saw that I was creating a new feature, and as soon as I was done, the fillet appeared. There's no version skew, no emailing files back and forth, just both users looking at the same model. So here's the big picture. Each box on the right represents a bunch of machines in an Amazon data center. And the boxes on the left represent the types of clients we support. In last year's talk, I described what all of these do, but for the fillet operation, only the blue boxes are involved. We'll start in the browser client and then talk about what happens in the modeling server, the geometry server, and the database. The web servers have already played their part in serving you the client, logging you in, and helping you find the document. This is an overview of the communication that happens between the client and the servers. Each arrow represents a message sent, and we'll get into the details of what they are. But even without these details, you can already see a few things. The first is that there's only one round trip from the client. This is important because this picture is not to scale. The round trip latency between the client and your modeling server depends on how close you are to our data center. For instance, when I captured the fillet video, I was connected to our data center in Oregon, and my latency from Boston was about 80 milliseconds round trip. The modeling server and the geometry server always live in the same data center, so the latency between them is vastly smaller. The second thing you can see is that the modeling server saves your edit to the database at the same time as the geometry server regenerates the fillet. This happens automatically, and this is why you don't need a save button in Onshape and why you don't lose data. If something goes wrong with regeneration and the geometry server crashes, that does not affect your edit. The third thing you can't actually see from this picture, but I'll tell you anyway. And that is that every one of these arrows only represents data that pertains to the fillet. We never send the entire model as part of the communication, and that is key to our performance. So let's start with the client, which is what you're looking at in your browser. In order for it to be ready to process commands quickly, it has a few things already loaded. It has a secure WebSocket connection to the modeling server, so they can communicate directly without any overhead. It has the tessellation triangles that make up the faces of the current model, allowing you to smoothly move the camera without having to go back to the server. Associated with each body, face, edge, and vertex is a short, automatically generated string that we call a deterministic ID, and it is unique within that part studio. You never see it as a user, but when the client wants to talk to the server about a concrete piece of geometry, it uses the deterministic ID. For every feature in the toolbar, the client has a description of what that feature is and what parameters it needs. We call this description a feature spec, and it's automatically generated from the feature script code that defines the feature. Feature script, by the way, is a programming language that we created, and we use it to develop our features, and you can use it to make your own. In the case of fillet, the feature script code lives in a public document called std, which is our standard library. And this feature spec is used to construct the dialog that lets you specify all the fillet options. The client also has a list of all the current features and their parameters in memory, so you can edit them quickly. So when you click fillet, the client uses the feature spec to construct the fillet feature with all of its parameters. That fillet feature includes the deterministic ID of the edge we selected for filleting. And then the client sends a message over the WebSocket to the modeling server saying that it wants to add the new fillet feature to the end of the feature list. And now Lana will talk about what happens on the modeling server.
Every client connected to this document communicates with the same modeling server. In this case, there are two clients working in this workspace with this part studio simultaneously. Messages from the client to the modeling server are serialized, compressed, encrypted, and signed to keep communication secure and efficient. Here, the modeling server receives a message to add the fillet feature with parameters and edge selection information. Notice that we do not send the entire model definition from the client to the modeling server, but only an incremental change. There are two reasons for it. Performance, of course, but also collaboration. If two clients are adding features at the same time, they don't override one another's changes. Also notice that the clients are sharing the same modeling server, rather than each getting a separate copy of the service. This is called multi-tenancy, and is the core of Onshape design. The modeling server holds the latest state, the only source of truth. The changes made from different clients are integrated and communicated to the database and to all clients. As Ilya mentioned, on the client side, all selectable geometry has deterministic IDs. Let's say it's F for the edge to be filleted. Such an ID is meaningful only at the state in which the selection is made. A slight geometry change and that ID is gone or attached to another geometry. It wouldn't work as a persistent reference we need to save with the definition of the new feature. That's why the process starts with the modeling server asking a geometry server to generate a robust reference for edge F. What do we need by the robust reference? Let's consider the requirements. For example, this edge reference needs to be robust to removing fillet 1. Your collaborator might be inserting a chamfer while you are adding a fillet. The reference needs to be robust to removing material or adding material. This set of requirements is not specific to Onshape. Every parametric CAD system needs a mechanism for referencing geometry in a way which is robust to changes high in the feature list or configurations. Users of parametric CAD expect to be able to roll back and forward in the feature list, to edit feature parameters, and to insert and suppress features. More generally, because Onshape part studios can produce multiple parts, we require robust references not only within the same part studio, but in derived part studio assemblies and between documents. Use of configurations places high requirements on quality of robust references. Onshape configurations allow infinite permutations. It is impossible to test all of them, but we need to be confident in the references holding up. In summary, a robust reference captures the identity of a geometric entity. And this is where we are in the process of adding a fillet feature. The modeling server is asking the geometry server to generate a robust reference for the selected edge. A geometry server serves one part studio. Its state always corresponds to a particular state of that part studio. It exists to provide the modeling server with information. The part studio geometry server receives the part studio definition, its feature tree and part properties, and uses it to construct the geometry state and tracking information. To represent the geometry state and perform geometry operations, Onshape uses Parasolid geometry kernel. Parasolid is a software component developed by Siemens Digital Industries Software, and it is the industry leader in geometry modeling. The tracking information is what will be used to generate and resolve robust references. This process of reconstructing geometry and tracking data is responsible in response to definition changes is called regeneration. There is a requirement specific to Onshape. Regeneration has to be deterministic, which means that the same model definition has to always result in the same state of a geometry server. This is necessary to support collaboration, branching, and merging. This is also necessary for configuration correctness. Such a requirement means that the regeneration of every feature can depend only on the state created by the feature before it and its own parameters. There can be no dependency on what happened the last time when the feature was regenerated, because there is no concept of the last time. The determinism requirement dictated the design of Onshape's robust reference solution. The identity of each geometry is established by its history. A sketch curve identity is linked to the user action when sketching this curve. For example, drawing a rectangle produces 4 line segments. When regenerating any feature, we keep a record of all geometries created by it and track their dependencies. You can see here snippets of history records created by sketch, extrude, and fillet. We link extrude face identity to extrude feature ID and sketch curve defining its geometry. Those identities can be traced through the later features that you can see here. Extrude identities defined this way are also robust to sketch edits. Notice that this sort of parameter changes is what configurations would typically control. Let's talk a little about the quality of robust references. You've likely seen models behaving this way, fillet splitting faces in the areas of high curvature, or shell doing whatever it takes to produce inner faces. Very small parameter changes can cause those faces and edges to exist or not. If they are used as references, the model becomes unstable to small changes. If we configure parts using such references, we cannot be confident that every configuration will regenerate correctly. Thinking one step further, because we know that fillet and shell can behave this way, we should be careful not to reference geometry they create unnecessarily, even if geometry appears regular. As always with parametric modeling, one has to consider the design intent. Geometry, which can be linked to the design intent, makes for more stable references. So back to the filleting this edge. We are interested in the edge F. The identity of the edge shared by 2 extrude side faces is defined by both of the sketch curves used to create the faces. The robust reference combines edge F record and the records of 2 sketch entities into a feature script map, which we call a query. Those familiar with feature script know that a query is the way to reference a model geometry in feature script. From the feature script point of view, this map is just another one of query types, a historical query. The new query is converted into a compressed string and sent back to the modeling server. And Ilya can tell you what happens next.
So to sum up, the client has asked to add a fillet. The modeling server asked the geometry server to make a robust reference to the edge being filleted, and the geometry server responded with a query. And now we're back on the modeling server. At this point, we're ready to save the edit to the database. We will do that by creating what we call a microversion for the Part Studio, a snapshot of the new feature list that includes the fillet. There is a special object in the modeling server that manages this process, and it's called appropriately the Microversion Manager. And it is necessary because, like everywhere else, we don't want to save the entire Part Studio every time, just the stuff that changed. In this case, the new fillet. And the job of the Microversion Manager is to keep track of these changes and put them together when necessary. So we will write that a new fillet was added as a new microversion in the database. At this point, we'll also update the references in the workspace if the part was used in an assembly or derived into another Part Studio, and we'll create a new document history entry. Now, none of this requires any geometric computation. We're just writing data to the database. And after this point, if something were to happen and the geometry server were to crash, or you lost power to your computer, or the modeling server were to disappear, which happens rarely, but it does happen, your changes are still saved. And at no point in this process is the database in some sort of intermediate invalid state. At the same time as this is happening, we're also sending data about what's going on to our logs, sending performance information to our monitoring systems, and if you're in an enterprise account, sending information that you created a fillet to our enterprise analytics. Now, none of the data accessible to us as Onshape developers captures geometry information as part of our deliberate effort to protect your IP. So our logs will record that you created a fillet, but not where or what kind or how big. Let me talk about microversions a little more. A microversion represents a snapshot of the whole Part Studio. So given an idea of a microversion in the database, we can reconstruct the whole feature list. But it's stored just as an edit. So the microversion we just created would have the ID of the parent microversion and the change to add the fillet. If you're familiar with Git, this is very similar to how Git commits work. Now, the most important thing about microversions is that they're never modified once created. Whenever you edit the Part Studio, we'll create new microversions. And this gives us several advantages. First, we avoid overwriting data in the database, reducing the risk of corruption. Second, we keep around all previous states of the model, giving you access to old versions and the ability to restore to an old state if something goes wrong. And third, it simplifies our internal logic because a microversion ID, possibly with a configuration, is all it takes to specify the exact geometry of a Part Studio. And this forms the basis of referencing and collaboration as we use microversions to keep track of what each client is looking at. As I mentioned, each microversion has a parent. So you can think of the microversions of a Part Studio as a tree with branches like shown on the right. And this structure forms the basis of our branching and merging. And when you use our API, you need to specify what you're reading or writing in terms of microversions. So microversions are one of the most fundamental concepts in Onshape. Okay, back on the modeling server, we just created a new microversion with the new fillet in the current workspace. All of the connections to clients in that workspace are listening for new microversions. So both client connections get notified that a change has been made. The client connections will immediately update the feature tree with the change, but to update the rendered model, it needs to be regenerated and retestylated. So both client connections will ask the geometry server to do that. The geometry server has the feature list already, so we just need to send the additional fillet, not the whole model. And because both clients are asking for the same microversion, we only need to do one regeneration. And in some cases, most often with assemblies involved, we can do regeneration on multiple geometry servers in parallel. So let's take a step back here. This is the essence of a single source of truth. A new microversion is created in the database, and all clients immediately see it. The other cool thing is that none of the code involved here knows anything about fillets. It's just responding to some change in the model, and other edits like suppressing a feature or editing a sketch dimension or changing a configuration table are all handled the same way. So when we develop new functionality, we usually don't have to worry about this stuff, letting us move quickly. And now Lana will tell us what happens on the geometry server.
Now the modeling server asks the geometry server to give it tessellation and feature regeneration reports at the new microversion. The geometry server is sent the definition increment. In this case, add fillet to instruction. The increment is analyzed. In this case, a new feature is being added, no rollback is required, and regeneration starts at the new feature. If we were editing extrude 1, we would have rolled back to before extrude 1 and regeneration started there. If you recall, our features are written in feature script. So regenerating fillet feature means executing this block of code, which is the definition of fillet in the std library. Internally, the geometry state is a brep represented in the parasolid kernel, and each geometry change is achieved by a call to its corresponding parasolid API. Brep is short for boundary representation. A model is represented by its boundary. A part consists of faces. Faces are defined by their surface geometry and boundary edges, and so on. By the way, because Onshape uses parasolid, there is no approximation data or data loss when converting to and from other parasolid-based CAD systems like SolidWorks or NX. After the incremental regeneration, we determine what geometry was touched by regeneration and update tessellation only for that geometry. In this case, the green face was added and the blue faces were modified. Tessellation quality is automatically defined based on the scene complexity or can be explicitly controlled by the user. As soon as a new tessellation increment becomes available on the modeling server, all the clients connected to this part studio are updated.
So now that we know what happens behind the scenes, let's watch it again in slow motion. The user just clicked, the dialog is created, and the collaborator is notified of the new feature. And the preview appears after a round trip to the server that we didn't discuss. Now the user clicks OK. The dialog disappears, a microversion is created, and the collaborator gets the new feature, and finally the graphics. And that's the whole picture, at least at the level of detail that we have time for today. You added a fillet, and after a trip through the modeling server and the geometry server, you can see the results. Let's sum up. There's a lot going on to make even simple operations happen. Some of it is similar to what you'll find in a professional desktop parametric CAD system. For example, all such CAD systems have some way of robustly referencing geometry, typically based on the parametric history. And all such CAD systems rely on a BREP geometry kernel for the basic operations. But there's a lot that is very different also. Our data is stored in an encrypted, backed up database, not a file on your hard drive. Our version control system is baked in at the very foundation of Onshape, not tacked on as an afterthought PDM system. You also saw how we fully support multiple users simultaneously working on a document by leveraging our multi-tenant architecture. Feature script is also something that's unique to Onshape. In other systems, first-class features can only be developed by the vendor, while in Onshape, you or a contractor you hire can create them. And all of these differences that you've seen at work today, through the lens of the add a fillet operation, translate into the benefits that you're used to in Onshape. Thank you.
Great talk. We do have some questions on the line, so I'll get started with one coming from Michael Pasco, who asks, what are some of the key differences between the opening Apart Studio with the Onshape iPhone app and the desktop browser?
Lana, would you like to take this one? Or?
Yeah, I can. So the difference is only on the client side. The clients are written differently because our mobile clients are optimized for the mobile hardware. Otherwise, they would talk to they would talk to the servers through the same WebSocket, and using the same encrypted messaging system. So as soon as data leaves the client, all the process that we've traced through today applies to the mobile, whether it's mobile client, web client, or whatever client we come up with next. Do you want to add anything?
No, that basically covers it. Essentially, yeah, there's no difference almost as far as the server is concerned. In some case, if the mobile client is a little bit older, the server is aware of it and can adjust some of its messaging to be able to work with an older client. But basically, mobile clients and browser clients can all collaborate together.
Great. There is another question from Evan. He asks, does multi-tenancy mean the collaborators across the world are sharing a server instead of using the closest one?
Lana, you or me? Me? Okay. So not necessarily. In our case, it does. Right now, if you've got collaborators across the world, they will be talking to the same modeling server in order to keep the access to the database synchronized. This is, in the future as we scale, this is something that we hope to be able to get away from. Lana, do you want to add anything?
Yeah, I'll add that there can be sort of passive collaboration. For instance, if your collaborator works on a different document but links your document, links references from your document, then in order to serve data for the linked document, he would be loading it read-only on a closer server. That's why sometimes in these scenarios, we advise that people start referencing data through versions rather than within workspace.
Right, to avoid the latency of going across the world in that case.
Excellent. Nick asks, is there a way to interrupt the message flow process on a fillet that is taking too long to generate? It's common for me to add fillets to organic shapes at the end of the tree. I have experience trying to add fillets that don't show, that basically fail and take a while to generate before the preview is pushed.
Lana, you or me?
Yeah, I'll take this one. So yeah, that's something that we would very much like to do. It proved to be somewhat difficult. But it is on our radar. Right now, we don't have a way of interrupting fillet. What you can do is undo and reload. And that and that might save you waiting time, might not. Depends on scenarios. You want to add anything?
Yeah, one of the things that we do if you do pile up multiple fillets is we will, if you have multiple changes queued up, we're not going to regenerate all of them in sequence. We'll jump to the latest one. So we can skip sort of to a final state. Obviously, if you have a single fillet that is taking significantly longer than necessary to regenerate, that doesn't help. But in a lot of cases where fillets are just taking a few seconds each, that can be helpful.
Great. There's a question that follows along this string of thought asking, is there a way to force a full regeneration from the top of the tree? As sometimes I come back to a broken feature tree, I'm assuming that the termination regeneration is rebuilding models somewhat differently from my previous sensing in the document.
Lana, you or me?
Yeah, I can do that. So tweaking the very first feature in the model tree will get you that regeneration. I cannot come up with a more direct way of doing that. You shouldn't have to do it. If you feel like you need to regenerate from the start, chances are something went wrong.
I would actually recommend if you're finding a model where you somehow come back it's in the wrong state and you have to regenerate, that's worth contacting support about. This does not happen, and regeneration from the beginning in a lot of cases is going to give the same result. So
or should, if all the determinism we talked about is right.
Great. Aaron asks, or he states, I love being able to collaborate with others simultaneously on part studios and assemblies. Is this functionality that will be coming to drawings in an upcoming release?
I'll take this one. So we can't really comment on when functionality will be released. This is something that we would like to have for drawings, but that's about as much as I can say. The sneak peek later on is kind of the only view into future functionality.
Great. A user asks, you talked about part studios. Do assemblies and drawings work differently?
Lana, do you
Yeah,
mind?
I can take this one. So yes and no. From the high level point of view, when we talk about how data is persisted in the database and how data is structured in microversions, they are identical. But the content of that data is different. The important difference between Part Studio and assembly is that Part Studio exists and can exist independently of any other elements, while assembly requires Part Studios to feed parts into it. So assembly has references into Part Studios. If you, another significant difference between Part Studio and assembly is that Part Studio is algorithmic. It has this sequential re-execution, if you want to look at it from programmatic point of view. Assembly doesn't have that. Assembly is variational. Everything that's present there is solved as the same system and placed as the same system. That's one of the reasons why there is no feature script for assemblies. When working within workspace, any change in Part Studio is propagated to assembly immediately. When if we look at the drawings in this respect are more like assemblies. They have to reference a part studio, but their changes are not propagated immediately. The UX has made the choice that drawings are being updated explicitly. There is another slight difference with drawings. The WebSocket through which client communicates with, with the element, in case of drawings, connects to a drawing server. So there are differences in details. And do you want to add anything?
I would just add that last difference is part of the challenge in making drawings fully collaborative, because that drawing server is not, it needs to fully support the simultaneous collaboration.
Excellent. John asks, what is happening behind the scenes when the client makes a change? The change renders, but the wait dialog remains on the screen after the operation is seemingly complete. By the wait dialog, he is referring to the ping wheel that is running.
Lana,
hear you.
Yeah, I can start this. So as Ilya mentioned at some point, if there are you're making a change in Part Studio, if there are assemblies in the same workspace referencing this Part Studio, once the change in Part Studio is computed, assemblies are updated. So you might have noticed that actually there are two pinwheels, a small one and a big one. Or you are lucky and you never made a very slow operation. The small one goes away when Part Studio is fully updated. The big one goes away when the workspace is fully updated. So you should be able to work on your next operation once the small pinwheel went away. Do you want to add anything?
No, that's about right. That's my understanding of how it works as well.
A user asks, what is the difference between versions and microversions?
Lana, me or you?
Go ahead.
Okay. So let's see. A microversion is primarily an internal concept. This is something that we create, but we don't really expose it to the user. The closest we come to exposing it to you is the document history that you look at is actually a list of microversions for the document. A version is a point in time where you, the user, said that you would like to create a version. And inside, a version is just a glorified tag on a microversion. It's just a pointer to a microversion. Now, on top of that, a version has its own metadata and can be used for release management. And of course, it can be referenced from other documents, unlike an arbitrary microversion. But at the end of the day, a version is just a fancily dressed up microversion that has a specific name and has a little bit of extra stuff with it. Lana, did I cover that?
Yeah, I have nothing to add.
Excellent. Kurt is asking, why is there no rollback bar in the assembly tree, just like there is in the part studios, as sometimes it is easier than suppressing everything below a certain point?
Lana, me or you?
Yeah, I can take a stab at this one. As we've discussed, the feature tree in Part Studio is more of a feature list. There is a sequential regeneration of the features. So there is a clear sequence of what happens in what order. In assembly, even though the tree is presented as a list, it is a tree. It can be viewed as a duck. It's not. There is no sequence to it. So we could have a convenience a convenience tools allowing you to select a lot of stuff or make a selection saying suppress things under this, but that's all there's going to be. It's just the reflection of how things are rendered in user interface. It's not the same meaning as a rollback bar. And I think I wouldn't want to have a rollback bar there just so that concepts are not getting confused. But yes, please file an improvement request, and we'll see how we can improve the user experience there.
So I would I'd add that for Part Studio rollback, both the geometry kernel and our own, for example, history records that Lana talked about have special support to make it really fast to be able to go back in time. This is why rolling back and rolling forward, for example, is typically faster than actually regenerating, like after a change. Within assembly solves are typically a lot faster, and so that's not necessary. This is part of why Lana says that rollback is kind of a different concept than just simply suppressing the last 10 features. You could probably get so reordering features in an assembly doesn't change the assembly, whereas reordering features in a Part Studio will change the Part Studio. So kind of the tail end of an assembly tree is much less meaningful than the tail end of a Part Studio feature list.
Great. Another user is asking, do you have any best practices to make custom features more robust as we build references?
Lana, this one's for you.
Yeah, this one is for a long workshop and another year. I'll focus on one of the aspects of how to deal with robust references in custom features. When you write feature script, the references that the queries that people typically use are very dependent on the state on the geometry state. The typical references would be edges around the face, or edges parallel to certain direction, or faces of above certain size. That's all makes sense only at this point. As soon as any geometry changes operations are performed, that stops being a valid query. So something that before operation evaluated to a face or to a geometry might stop evaluating after that. Even if you evaluate before operation, you get so-called transient queries. And as the word suggests, they're transient. They have a chance of disappearing as a result of operation. That's why there is a very helpful little function called make robust reference, which is very nice to use in order to, sorry, it's called make robust query, which is very nice to use in order to trace identity of the geometry through operations. And it makes use of the same tracking mechanism that we've discussed earlier today that is used for resolving queries. And the same notion of identity that our queries have. And I think I'll stop at that because we are running out of time.
One last question, maybe we have time. It's kind of a big one, so hopefully we can keep it brief. But James asks, how easily would it be to replace Parasolid with a different geometric kernel? Is there something special about Parasolid that enables collaboration in Onshape?
Oh, I can take this one. It would be extremely difficult to replace it just because replacing a kernel in any CAD system is an extremely difficult undertaking. Essentially, you're writing a lot of at least half of the CAD system from scratch, because the APIs are different. Also, you can never remove Parasolid from Onshape because your customer models have to continue regenerating, and any other kernel is going to do regeneration slightly differently, but even slight differences in regeneration are going to break everything. As far as collaboration, I don't believe there's anything special in Parasolid that specifically enables collaboration. And, if we thought, for example, that ASYS was a better kernel, we could have written Onshape around ASYS rather than Parasolid, but we did not. And I'll add there's currently no plan to replace Parasolid in Onshape. Lana, do you want to add anything?
Yeah, it would be almost as easy just to write a new CAD system based on a different kernel with the same collaboration properties.
Wonderful, thanks.
All right, it sounds like we're out of time. Thank you very much.
Thank you.